Hello and welcome back to another video on my channel. Yeah, it's been a while. I don't know how that happened. So anyways, I'm happy to see you. I don't actually see you. But anyways, I'm still happy. So I thought I should maybe do at least one video in 2021.
You already did one.
What?
You did one already.
Oh, it's my second video of 2021. Just kidding. Of course I don't know when this is gonna be released. So last time when I was driving back home after visiting a friend, it was evening, I was listening to music and everything. Can you please turn down the music? Thank you. So anyways, it was evening, I was listening to music and everything was just relaxed as the night slowly set in. And I thought about how I should do road trips more often. However, considering the rising gas prices, cost for maintenance and also the environment, I thought that there must be another solution to unwind. So if we can't get out into the world, let's instead spend hundreds of hours developing, understanding and debugging a program which in the end brings the world to us. Sounds fun? Yeah, you bet. And totally not boring. You get the idea. I want to make my own kind of driving simulator where I can drive and walk around virtually. And also, since I'm lazy, add a lot of automatic processing and throw everything into a game engine. You know what? Let's just try. First of all, we need some terrain data, because without terrain we have nothing in our game or simulator to drive on. Oh yeah, I also would like to use real-life terrain data, not procedurally generated one. We're building a realistic simulator after all. How hard can it be to get some terrain data? I mean, it can't be that hard, right? Okay, maybe I underestimated the whole thing a little bit. There's different ways to approach this. So option number one would be to go out and measure each street, each hill, each mountain, lake and building for ourselves using a tape measure or a ruler and note everything down. But since that doesn't sound very comfortable at all, again, I'm lazy, let's opt for option 2 here, which is relying on readily available data. So for once, we could use the elevation data from Google Maps, that, you guessed it, Google even uses for its Google Maps service. Or we could also pay for some LiDAR scanned area point clouds, which have very high accuracy, but also which there are sadly none of in the area where I live. Also, it's right now impossible to capture the whole world, maybe in a few hundred years, if we still exist then. Anyways, since I'm a college student, which also implies that I'm broke, I figured that it would be best to take one of the other options. So first, we could also use OpenStreetMap's elevation data, but to be honest, I found that one to be a little on the inaccurate side. Okay, so you won't believe it, but the other day I found this mysterious website here that somehow can give us varying elevation data on points as close as 10 meters apart. They seem to use the source Merit-Dem, whatever that is. And after some research, it turns out that the project Merit-Dem, or Multiarrow removed imported terrain digital elevation models, yeah, a very handy name, and it took me a few attempts as well, was developed by students at a Japanese university, where they took existing elevation models from NASA and others, and they built a program which removes errors caused by trees or obstructions like buildings automatically. We can now take this data, let it process and convert it into an OBJ file, which we then can load into a game engine. Sounds easy already? Exactly. Let's go. First of all, we ask the user for the exact coordinates that he wants to map. We then quickly check the values and also see if they make any sense. Next, we try to figure out the correct file name. The files that Merit-Dem provides are labeled according to their lower left corner, so for any given coordinate, we need to find the nearest lower integer ending with either a 5 or a 0. We then figure out the correct cardinal direction, according to if the coordinates have negative or positive values. Lastly, we assemble the whole file name and give the user the option to overwrite the file name, if necessary. Next, we import Geotiff, which is a library for reading Geotiff files. Geotiffs are like regular TIFF image files, but they also contain metadata about the area they cover and the coordinate system that they use. They also can have different layers, which are called bands. We then load the file in our coordinate system. This will be important later. We also read the shape, which means we read what width and height the file has. Next, we see if the file contains the necessary data. If the file doesn't contain the necessary data that the user wants, we quit the program. If it does, we continue and fill an array with the data. Okay, so this next step is very crucial to understand. Since the world is divided into degrees, the distance between latitudes, indicated with the red arrows, will be always the same, so they will be equal. However, the distance between longitudes will be less the closer you get to the poles and will be higher the closer you get to the equator. so they are not equal. Okay, but why is that a problem? Because the Geotiff files are always at a fixed 6000 by 6000 pixels. That means some need to be stretched, while others don't. So we need to apply a scaling in a very specific way to all the Geotiff files in order to get a correct OBJ file out of it, which corresponds to real-life dimensions. And that's exactly what we do in this code snippet. First of all, we define fixed values of the circumference of the Earth around the equator, the radius of the Earth at the equator, the circumference of the Earth around the poles, and the radius of the Earth at the poles. We need separate values because the Earth is not a perfect sphere, but almost. We also define a function which converts any given degree value into radians, which will be used later on in the sine function. To calculate the distance between one and another longitude, we take 5 over 360 times the circumference of the Earth at that place, which can be calculated by the sine function. We do that for both the upper and the lower boundary, and then calculate the median. We also calculate the distance between one and another latitude, which always should be the same, so it should be a constant. At the end, we just print the result and convert it into meters. Okay, that was a lot of theory. Let's finally get to the point where we can actually see something. Alright, time for a quick recap. We have figured out the correct scaling, and we have the elevation data stored in an array, where all the values are in meters above sea level. Let's finally get that information into a sweet OBJ file. And what should I say? After reading through the OBJ file format specifications, I understood nothing. However, I did figure out how to store points, also called vertices, in 3D geometry. It's literally one of the easiest examples. So let's just export a point cloud for now and revisit this issue later. And actually, this is not very hard at all. You just need to remember to awake the ancient spirits, ask them to write the whole code for you, and then put them back to sleep. Also, just for good measure, we make a routine that does absolutely nothing. And since I would feel bad about letting you wait, I actually started the program in the past, and look, now it's ready. If only everything was that easy. So if we have a look at the file in Blender, we can see nothing. Well, to be fair, I don't know what I expected, but this looks a bit grainy and a bit hard to drive on. But if we actually connected those points with faces, I could imagine it looking way better. Okay, time to dive back into the OBJ file specifications. Okay, I'll try to go over this quickly. Imagine a coordinate system in X, Y, and Z direction. Now, if we wanted to build a simple plane, we'd have to define each corner, the normal vector, and how to connect the faces. The normal vector displays where the outside of the mesh is, and it's a unity vector, so it always has the length of 1. When defining the faces, we not only have to specify how to connect the points, we also have to tell which normal to use. In this case, it's 1, because there only is 1. Now, if we wanted to add a second plane, we would have to add 2 points, but also another normal, so for every face there should be a normal, if the normal of another face is not directly applicable to this face. And if we have a look at the file size of the already existing point cloud file, it might become clear that by defining another few thousands of normals, we not only increase the used disk space, but also the loading time of the OBJ file. But there is another solution. The OBJ file format allows the polygons to be connected in a counterclockwise way, so that a 3D program always knows where the outside of the polygon is. And here's my idea. In our world, because there are no overhangs, there's just terrain, which can be mountainous or flat, but the outside is always upside. So it should be relatively easy to make a program which can define the faces counterclockwise, and thus suitable for 3D rendering. So now we not only write the points, but we also connect the faces. And after what felt like an eternity, let's see the results. Wait, let's first have a look at the file itself. Wait, why is face number 2 and 1 connected to 320,801? Okay, obviously there's a mistake somewhere. I want to see what that looks like. Alright, give me a second. So before I open the file, let's first get ready and relax and get ready just to embrace the full beauty of this file. So we're seeing a beautiful part of France, obviously, with its romantic green meadows and fields and blue skies. So what is it gonna look like? Well, all I can say is stay tuned for part 2. Goodbye, see you next time.